Hi everyone, my name is Strong Liang. I'm going to talk about protecting intellectual property in additive manufacturing systems against optical side-channel attacks. This is a joint research effort with Professor Rahim Beyer in Georgia Tech and Professor Salman in Rutgers University. So, what is additive manufacturing? Additive manufacturing, also known as 3D printing, refers to a collection of manufacturing processes where materials are joined together layer by layer to make objects directly from designs. Additive manufacturing is gaining popularity in critical industry such as aerospace, automobile, medicine, and construction. As additive manufacturing finds more applications in critical industry, cyber attacks on additive manufacturing systems are increasing. There are research efforts in the literature to explore the possibility of side-channel attacks to steal intellectual property in additive manufacturing systems. So, for example, by listening to the noise in a printing process, many researchers were able to recover the printing paths of the object. In general, intellectual property in an additive manufacturing system refers to any information about the object to be printed. Intellectual property can be very valuable in an additive manufacturing system, just like data are very important in a computer system. There are many different forms of intellectual property. So for example, the intellectual property can be the 3D design of the object. It can be the G-code instructions, which are directly understood by the printer. It can be the layer trajectories or the layer paths, which can be easily visualized and inspected by human beings. Or it can be the state variable signal. In this case, it refers to the coordinates of the printhead over time. So instead of performing acoustic side-channel attacks, we focused on something else, namely the optical side-channel attack. So this is actually a threat model for general side-channel attacks. So we have a printing process and we have an attack process. For the printing process, G-code instructions are sent to the printer for execution. Various actuators in the printer move according to the G-code instructions, and an object is printed as a result. Meanwhile, various kinds of side-channel signals are emitted into the space. In the attack process, sensors are used to capture the side-channel signal in the space. The side-channel signal is then analyzed by machine learning or signal processing to recover the state variable signal. The main difference between the acoustic side-channel attack and the optical side-channel attack is the sensor, the side-channel signal, and of course, the techniques to analyze the signals. When performing an optical side-channel attack, the question is, how do we obtain the optical side-channel signal in the first place? So there are at least 3 different ways to do this. So first of all, some additive manufacturing factories may have surveillance cameras for security purposes. It is possible for these surveillance cameras to be connected to the internet. Hackers may then able to get into those cameras and to get a video feed. This can be possible as demonstrated by the existence of botnets in surveillance cameras. Second, it's possible for the attacker to exercise social engineering. So maybe the attacker might be able to get a maintenance guy into the additive manufacturing factory and secretly install a camera on the ceiling. Third, many printers have built-in cameras for process monitoring purposes. So, for example, Ultimate 3, a very popular 3D desktop 3D printer, they have internal cameras for process monitoring purposes, and this printer doesn't require authentication to view the video from the camera. However, if you want to see other parameters inside the printer, or like if you want to make changes to the printer, authentication is still required. This is an overview of the optical side-channel attack. The attack is performed by machine learning. As with any machine learning process, there are 2 stages, the training stage and the testing stage. For the training stage, the main challenge is to obtain the training dataset. So the attacker might be able to get the same printer in a very similar environment. Then the attacker can ask the printer to go to a specific location, take a picture and use the location of the printhead as a label for the picture, and repeat the process over and over again automatically. To diversify the training dataset, the attacker can nudge the printer a little bit, can nudge the camera a little bit in the process. We can also apply data augmentation to further diversify the training dataset. So with the training dataset collected, we are ready for training the neural network. So here, we use a modified version of ResNet 5.0. ResNet 5.0 was originally designed for classification purposes. We modified ResNet 5.0 into a regressor. So instead of having 1,000 classes as the output, this modified ResNet 5.0 has three numbers as the output, namely the x, y, and z coordinates of the printhead. In the testing stage, the attacker takes out images from the video frame by frame. Each image is fed as input to the neural network. The neural network then predicts the coordinates of the printhead. The coordinates over time form the state variable signal. So this is the experiment setup we created to test our proposed optical side channel attack. We collected a total of 180,750 images for training purposes. The figure on the right-hand side actually shows the training process. The loss here is actually the average distance between the actual position of the printhead and the predicted position of the printhead in millimeters. So we can see that the training process converged. So with a neural network trained, with a trained neural network, we perform some tests on some real printing processes. So the first row shows the ground truth trajectories for 8 different objects. The second row shows the recovery trajectories for the 8 different objects. And we can see that overall, the neural network was able to properly recover the printing paths for a variety of objects with different sizes. Nevertheless, the recovery is not perfect. So for example, we can clearly see the distortion in the recovered turbine. So what about different layers? The neural network was designed to recover the trajectories in the three-dimensional space. So we can see that the neural network can properly recover the trajectories for different layers. So we saw that the optical side channel attack could be performed for real printing processes, and that is a concern. To defend against optical side channel attack, we look into the optical noise injection method, which is an effective method with a low overhead. So the basic idea is to use a projector to artificially inject optical side channel signals into the printing area to make the side channel attack harder. The input to the projector is known as a noise pattern, and it can play a very important role in the optical noise injection method. So first and foremost, there is a limitation for optical projectors. So basically, it is possible to put any color as an input to a projector. However, due to the limitation of the optical projector, the range of colors, also known as the gamut, in the physical world is limited. So we can think about this in another way. If the projector has unlimited capability, it is possible to arbitrarily manipulate the image seen by the camera however we want. We can make the whole image a constant color over time, and thus totally eliminate the optical side channel attack. But this is not possible. So the question is, with limited capability, what can we do about the input to the projector to maximize the protection of the intellectual property against the optical side channel attack? So we're looking into noise patterns. There are 4 existing noise patterns, and they are replaying, random blobs, white noise, and full power. Replaying is basically to play the video of another printing process. For random blobs, we basically play large blobs with random colors and locations. White noise, the color of each pixel is obtained by sampling a random variable of a uniform distribution. and full power. All the pixels take the brightest color, namely pure white. In this way, the projector allows most of its power to be injected into the printing area. In addition to the existing 4 noise patterns, we propose 3 novel noise patterns, and they are channel uniformization, state uniformization, and state randomization. The idea of channel uniformization is to make pixels in a single frame as close to each other as possible. In other words, we attempt to even out the signal along the channel axis. For state uniformization, the basic idea is to make a pixel for different state variables to be as close to each other as possible. So as you can see, for a single pixel here, its color is dependent on the state or the state variables of the printer. By projecting a certain noise pattern, the colors of the pixel for different states are now more uniform with respect to their state variables. This is why this method is called state uniformization. This can make it harder for the attacker to infer the state based on the observation of the color. If we can do this, a single pixel in the image will stay more uniform over time in a printing process. So this noise pattern is also known as time uniformization. Finally, the idea of state randomization is as follows. So for a given state, here is a picture, and this is the original picture. Now, we randomly choose another state, and we know its picture, and this is a target picture. So now, at this moment, we create an input to the projector such that the picture seen by the camera gets as close to the target picture as possible. So there are actually 2 things happening in this process. So one, the original picture is getting cancelled as much as possible. Second, the target picture is getting replayed as clearly as possible. There is an optimization process to make this happen, and you can refer to the paper for more details. So we projected the optical noise with various noise patterns into the printing area. So here are the optical side channel attack results for a naive attacker. So basically, a naive attacker is someone who is not aware of the existence of injected noise. And we can see that most noise patterns can defeat the attacker. So what about an advanced attacker? The advanced attacker can see the noise pattern in the pictures. The attacker wants to filter out the noise and proceed with the attack. For that purpose, the attacker somehow manages to get training images with the same noise pattern. However, we assume that for noise patterns with randomness, the exact details in the images are different. So for example, for white noise, the attacker has training images with white noise, but not the exact white noise in the testing dataset. The attacker uses the training dataset with injected noise to retrain the neural network, hoping that the neural network will somehow filter out the noise and proceed with the attack. So here are the optical side channel attack results by an advanced attacker. So we can see that the advanced attacker can defeat most noise patterns, except state randomization. So for state randomization, you cannot infer important details of the printing process, such as the number of teeth in the gear. So if the previous example doesn't convince you that the state randomization can withstand an advanced attacker, let's take a look at another example. So here are the optical side channel attack results by the advanced attacker for a key. And now you can clearly see that the superb performance of state randomization. Okay, so that's all. Thank you for listening to my presentation, and I'm happy to take any question.